So, good morning. My name is Rick Cox. There we go. I am the Director of Research and Technology at the Combat Capabilities Development Command Chemical Biological Center, the entity formerly known as ECBC, if you're familiar with Edgewood. We are under the Army Futures Command, and we are an Army laboratory. We are the principal non-medical materiel DoD laboratory for chemical and biological defense. Although we are an Army laboratory, we work for the joint program, so you've heard from both DTRA and JPO, which are our partners, and we support them. But because of our unique mission and our unique infrastructure and our history and our capability, we also support many other government agencies beyond the Joint Chem Bio Defense Program, other government agencies, private industry, and other nations as well. So we have a very broad array of organizations and entities we support based on our capability. And I think that gives us a unique perspective because we're really at the sort of the execution point. We're the ones with the hands in the lab, working with these materials, working with the sensors, working with the detectors. And so at the same time, we have visibility of all the different entities that need our expertise. So I think that puts us in a unique position, as well as integrating the warfighter perspective because we are an Army lab. So we're able to leverage that and I think provide great value, especially in the area of threat awareness.
Great. Michael?
Good morning. My name is Mike Walter. I'm currently a senior advisor in the Countering Weapons of Mass Destruction Directorate, I guess is who we are now. And I've had kind of a weird background, and I know I've been around here way too long because I know most of you, and I know most of the organizations that you're in, which is kind of scary, especially since I'm so young. So my initial assignment in DHS was actually running the BioWatch program. I was then transferred over as a senior advisor to the assistant secretary. I'm currently a technical advisor to BD-21, the BD-21 program. I'm also detailed to ASPR. I'm the biodefense coordination team representative for DHS in implementation of the National Biodefense Strategy that was signed out in May of 2018. And we've just finished our first assessment, starting the second assessment. And coming out of that was 4 priorities that were published or about to be published by the National Security Council, one of which is knowledge management and how do you deal with all this data. So this conference is actually right on target. It is a major priority. It is a major concern. And as of yesterday, I was informed that I'm going to be taking over oversight of developing kind of the next or the future technologies for biodetection and response, both in kind of immediately, short-term, and long-term. So I'll be kind of getting more into the research and development side, which is interesting for me because I've done a lot of that, but my frame of reference is actually very operational. So when I look at technologies, when I look at needs, I tend to look at technology, but also how do you apply them operationally and how do you make them make sense?
So no pressure here, but
it
sounds like you were you're the human duct tape on all the seams that Ed Lawson was talking about in the
that
previous.
That you poke holes in to kill them. Yeah, I'm the guy who gets poked in. Yeah.
Mark.
So I'm Mark Wrobel. I'm a research program manager with DARPA's Defense Science Office, DARPA being the Defense Advanced Research Projects Agency. Hopefully a few have heard of it. We are an organization intended to protect the U.S. from strategic surprise. So our research portfolios are vast and varied. I am in DSO, which is what we consider DARPA's DARPA, working on some of the hardest and most, I'll say, risky technologies, trying to advance U.S. capabilities in many different areas, focused heavily on fundamental and basic research, but in my particular case, it's very applied. I've been involved with a program called Sigma previously, came to DARPA about 9 months ago and took over a program called Sigma Plus. And Sigma was a program that DARPA feels was highly successful at demonstrating the capability for wide regional or urban scale monitoring for nuclear and radiological threats in a cost-effective and highly capable manner. Sigma Plus has now built upon that program, adding advanced sensing capabilities on the chem, bio, and explosives front providing a more holistic capability for countering weapons of mass destruction threats, and trying to focus not just at boom and response, but really moving the bar as far to the left of boom as possible. Developing sensors that are looking at indicators of potential adversary pursuit of WMD, and trying to do those interdictions and countering capabilities, again, well before an attack occurs.
Thank you very much. And before we get into some of the newer technologies, and I think we're going to spend most of our session on the data challenges here, but let me ask what might be a remedial question for some of the people in the room. We had previous speakers talk about new tools, new sensors, some of which can't be discussed. But let's talk about the current state of the art is. Traditionally, what is the, what are the tools for the sensor tools for monitoring? Because my understanding from our conversations is that for all of the data and all the technology, at some points we're still talking about essentially, filter paper that has to be pulled from the sensors and run to the lab.
So, I can talk from my perspective. I've been working with sensors and detection technology for about 20 years. The state of the art, I think, at the ground level really hasn't changed much. You're still talking about either point and use dated terminology standoff detectors. Mm-hmm. So these are single entities. They may or may not be networked. If we're lucky, they're networked. But a lot of the technologies have not developed over, say, the past decade. So you look at some of our IMS detectors. They're very good detectors. We have colorimetric detectors still. We're still using essentially pH paper in some applications, believe it or not. And that's okay, but I think we're at a point where we're looking at these and saying, how can we leverage those new technologies, new processing power and things like that to improve on these existing technologies? Again, they work, but they're not as easily integrated as we would like.
Right. Mike, anything you'd add there?
Yeah. I think the state of the art for biodetection right now is collect a sample on a medium, a filter, or a liquid, take it to a lab, and analyze it. That is state of the art. And I've gotten into an enormous amount of trouble telling various bosses that, because everyone seems to think it's either like Star Trek, so I've got a tricorder, or rad nuke, I can pull out a radiac or whatever and scan the ground and identify an isotope. And in the bio world, that doesn't work. And what our technology is quite literally is collect the sample, take it to a laboratory, and any advances that have been done in the laboratory in sample analysis. In BioWatch, the state of the art was a dumb collector, a portable sampling unit that's not networked, fairly, very, very sophisticated laboratory analysis, but it's PCR. And then for our IT infrastructure, it was, we had a website, we had email, and a conference call. That is the state of IT. So if you're interested in that area, you're in a nice place right now.
So, and Mark, obviously the work with Sigma and Sigma Plus is to move beyond, certainly beyond the conference calls and the website. Can you talk a little bit about how the toolkit's evolving, whether it's with the sensors or with the systems that are going to try and network them and make sense of the data?
Yeah, so it's very holistic in terms of the new technical approaches that we're investing in under the Sigma Plus initiative. So Sigma was enabled by networks and being able to, in real time, communicate not just dose rate or simple count rate data from radiological sensors, but full spectra, right? And when we talk about sensing, whether it's chem, bio, rad, when you're wanting to be both selective and sensitive, you want to have the power of that data, that power of that spectra to be able to analyze and deduce, is this something I really care about? Because in all of our spaces, chem, bio, nuke, rad, false positives are a problem, right? They're an operational issue. So we've really got to do things to tamp down nuisance alarm rates, false alarm rates, and ensure that we're still sensitive to the threat space. And whether we're talking about ion mobility spectroscopy or mass spectroscopy, Raman spectroscopy in the case of bio, gamma spectroscopy in the case of radiation sensing, taking those spectra and applying advanced analytics to those spectra is extremely powerful to differentiate threat from non-threat. But the networking enables much more than that, right? Because I can look at that sensor data over time, a single sensor, and say, what am I seeing over time consistent with a threat? Not just a single measurement, but many measurements over, say, seconds to minutes to hours. And it becomes even more capable when I start networking many sensors together, right? If I were to, say, have a nice IMS mobility spectra in a network of, say, dozens of sensors all reporting in real time, I can fuse that data with things like meteorology data and be able to do things like further tamping down nuisance alarm rates because my sensor readings are not consistent with what the weather is telling me. And I can do things like plume propagation to understand where other areas are being affected and calculate the source term, where that initial puff of release occurs. So these are the things that in Sigma Plus we're investing in, advanced algorithms through networking being applied at the sensor and the network level.
And, Mike, I'll come back to you in a second, but I want to jump to Mark on this. How does what... I'm sorry, I want to jump to Rick on this. Getting my dyslexia going here with the speaker list. Yeah. And, how is that working out in what you're seeing with your organization of trying to connect these disparate systems?
Yeah, so I'll build on what Mark said. Not just met data, but we're also looking at things like physical security data. So because we're developing these more advanced analytics and because we have the power often in the field to do the analysis, the processing power, we can start looking at maybe acoustical signatures. Does it sound like a WMD explosion? Without getting into too many details. We can also look at LiDAR. If your biodetector detects an event and it indicates there's a massive amount of particulate in the air, is the LiDAR you're already using for other purposes seeing that as well? And because in the past we haven't really thought outside the box, we weren't integrating all those different capabilities, all those different sensors, again, non-CB sensors, because we didn't have the power to do it. And it takes a lot of heavy lifting to integrate those in, but we now have both the computing power and the technology to be able to pull those together. It's still not a simple task. I think one of the previous panel members mentioned the curated data being critical to this. You still need to collect additional data. You still need to teach the system and develop the system, but it's possible now, and we're beginning to integrate those other technologies in.
And Mike, that's why I wanted to sort of jump over and then back to you here on this challenge of making sense of the data. You have to get accurate data, but you also have to be able to get these different systems to share. And you've had some experience with the challenges of that.
Oh, I have. And the challenge of getting these things to talk to each other is first of all, for Gen 3, for example, that was automating what we did, basically automating what we do in the laboratory. How do you come up with a network and you can transmit all of that data to somebody and make sense of it? Because what we didn't want to do, and I don't think we ever want to do, is take the human out of the loop. The idea was, and the fear was, this box is going to tell you you've been attacked and we're all going to respond like a bunch of mindless robots because the box said we've been attacked. And so the questions that we had was, when you network this stuff together, and we've talked about this earlier, you generate a tremendous amount of data. So my kind of approach to this was, picture yourself as a public health officer in Pittsburgh on Christmas morning at 3 a.m., and your PDA goes off, and it's the stupid sensor telling you that I think I see something. And what do you do? So what you don't want is this gargantuan data dump that gives you every CT value, every inhibition run, everything. What you need to know is, what do I need to know? Is this a problem? Do I need to respond to it or not? And going through all of that data and trying to figure out what's useful, what's reasonable, and what's actionable is deceptively complex. Because the tendency is more is better. Tell me everything. When I worked for JPEO and we were running the JSIP program, we put 6 laboratories on 6 installations, And every one of the garrison commanders said, I want to know the first instant you think you see anything on the bio side. So after about the third call at 2 a.m. saying, we think we see something, and the next call at 4 a.m. saying, never mind, they said, call me when you know you got something. Mm-hmm. And that's kind of where we are with this, is too much data, to somebody trying to make a decision is as bad as not having enough data because you're just blinded by it. So integrating all of this stuff together becomes a problem. And the other side of the equation is, when I was running BioWatch, I worked with 30 major cities, more than 30 major cities nationwide. And if you've been to one, you've been to one. Every city does it differently. Every city had their own common operating picture. Every city had their data needs. So whatever information architecture we put together and we try to field has to marry up to their systems. They will not make adjustments to their systems to match the federal government, because they put money into it, they know how to work it, they're ungodly conservative in changing, and they won't. So the challenge for us is, how do we integrate all of this information that talks to thousands of cities simultaneously, gives them what they need to know, and is still integrated with our needs so we can help respond?
So I want to come back to the interoperability of the systems here in a second, but before we leave the data overload question, Rick, the services have a lot of experience with biochem sensors in the field and trying to strike that balance between the annoyance of false positives but the complete unacceptability of false negatives. Yeah. Anything that you would add to what Mike was saying about how to strike that balance between alerting when you think versus when you know?
Yeah, I think it's a little bit, I don't want to say easier for DoD, but it is, but we still have huge challenges in that area, getting the various disparate portions to talk together. I think the situations are similar. In fact, you were mentioning on military bases. It's very similar. You're ultimately trying to essentially eliminate false negatives and pull out a signal and generate very low false positive rates. And it's about trust with your systems. And I guess all I would say is, in the past, I've visited installations where I saw a nice box that was a biodetector or chem detector that isn't used anymore and hadn't been used in 10 years. And it's kind of shocking when you see that, but when you talk to the people, they say, well, just like you said, after the third time, we shut it off, and we didn't know who to talk to. Mm-hmm. We didn't know who can explain this for us. And often it was, you drop a device in, you train the people on it, and in 2 years, that service member's gone. Yeah. And I know many of the services struggle with this issue. So it goes back to making those systems not necessarily invisible, but making them very reliable, very robust, and that's a huge challenge when you talk about the complexity of these, but give them as simple an answer as you can. Mm-hmm. And that's always a work in progress.
And Mark, with Sigma Plus, is it safe to say that one of the key goals here is by bringing in enough of the complementary data sets and improving the analysis, you can start to get to that right balance point of when to present the threat to a human and have them make that call?
Yeah, I mean, we're trying to generate information that's relevant and useful for the various stakeholders that we're engaged with in the development of the Sigma Plus capabilities. So having a common operating picture that is providing them that plume projection or providing them that track of a radiation source as it's moving through the environment with additional metadata about how do they interpret that. If we're, say, monitoring an urban environment, say, for radiological materials, and we get a cesium-137 encounter, there's a way I can fuse that data, say, with an NRC database that says, oh, yeah, that building next to you there is under construction, and there's a contractor there licensed to have cesium sources for non-destructive inspection applications. So bringing in these other contextual data sources, we talked about weather, but NRC databases, businesses that may have, in the case of chemical monitoring. So one of the things we're looking at that's a little bit different with chem monitoring in Sigma Plus is we're looking at precursors. This comes back to the question of how do we move to the left of boom as far as possible. So if folks are actually synthesizing an explosive or an opioid or an actual hazardous chemical, a chemical warfare agent, how would we be able to detect the fugitive emissions associated with somebody doing that, synthesizing these chemicals? But a lot of these chemicals are very much part of the background, part of the normal environment, just like radiological materials are part of the normal environment. So the algorithms and the fusion of contextual data needs to be smart enough to help inform those encounters, those detection events, again, to keep the operational burden down, keep the false alarm rates down, and provide actionable information to law enforcement and to other users of the technology.
So, and I want to ask Mike and Rick about the data source. We've talked about meteorological data. We've talked about sets from other agencies to know about the construction project. Ms. Richardson talked about social media when it comes to public health and bio. Are there other unexpected data sources that are being incorporated here?
Yeah, I mean, I can speak to at least one. We're looking at human physiological data. So I think someone mentioned, indicators of flu, and from the previous panel, you might not look at public health data. With the soldiers, of course, we have the advantage, less of the privacy issues. We can outfit them for physiological monitoring. And it may not be necessarily related directly to chem biodefense. Maybe it's just heart rate. Maybe it's just a Fitbit, a military Fitbit. And you get heart rate, temperature. Well, some of those things are very good indicators of illness, and illness is generally an indicator of a biological exposure, potentially. Mm-hmm. Of course, it's much more complex than that, but you can see there's a lot of power where we're looking at things you might not normally consider, and also leveraging things that are not chem bio specific at all, but with our chem bio knowledge, we can make them important to us in the chem bio realm.
And you talked about not only having those sensors, but having more processing power there at the endpoint.
Yeah, so one of the things we've seen, I mentioned like one of the pH paper examples. Mm-hmm. We're still using MA paper. We have the power now, and the expectation of the warfighter is that you will have some sort of processor in your hand, whether it's a droid device or whatever, some electronic device. Well, we can use that to interpret some of these things and expand the capability. So you can imagine a colorimetric array, right? It doesn't have to be one single strip of paper that changes color. Maybe there's all different types of chemistries. You can't interpret that with the naked eye, but you can easily snap a picture with your phone and use that processing power quite simplistically to give you an interpretation of that. I mean, that's a very simple example. You can see how this expands, where things we used to do in the lab, maybe 10 years ago, more so 20, we can do on a handheld device.
Okay.
And yeah.
It's damn depressing.
Yes. For those of us that spent many times at the computer processing spectra and looking at data, now you literally can do much more in the palm of your hand than we ever could. So we have a tremendous opportunity to leverage that power and put it right in the hands of the user, so they don't have to report all the way up, get all the interpretation. We can empower them to do what they need to do in the bounds of their mission.
Yeah, we sort of turned today's event into WMD in the age of the smartphone with the conversation today. But Mike, what data sources are you leveraging that one might not think about, or ones that you want to bring into the equation?
There are actually two that come to mind. One is, right now, in the event of an attack, we get a laboratory result in space and time. So we know when the sample was collected, we know where it was collected, we don't know where this thing came from. So being able to model in reverse, identify a source term, and then do a deposition model going forward. We can do that, but it takes hours to get it done. And we need it done quickly, and we need to be able to see it, because the thing that freaks people out on a biological attack is you can't see anything, you can't hear anything, everybody looks fine, and you have decision makers screaming to make a decision, and they're looking at a blank screen and they want to see something. And then the other part of it is more on the sort of the response side. So there's an attack, we do medical countermeasures. How do we know we're being successful? What are we tracking? So what data streams are there that we could identify that this would be perturbed in the event of an attack? Mm-hmm. This would, how it would be responding if we basically treated whatever the organism was, because it's going to result in some sort of a pandemic if we're not careful, or it's not. And we don't know what those data streams are We don't know what their normal backgrounds are. We don't know how to display them. So basically, the only way we have right now of knowing that, okay, it was Bacillus anthracis and it happened not to be resistant to ciprofloxacin, is we're not seeing very many people die right now because we got them the drugs and they took them. As opposed to, we're tracking all this, wait a minute, this isn't going down, and it's supposed to, we have an issue. And the other data stream is in the laboratories. It would be, what we get from public health is it would have been really nice. It's really nice. You told us we were attacked with Bacillus anthracis. It would have been nice if you had told me it was resistant before we gave out all those doses. So then the only way we can really do that is going into the sequencing realm. And the big thing there, besides just doing the sequencing, is how do you handle all that data? And by the way, you've got 6 hours to get it done because that's what it takes us right now. And make that operationally. So I'm glad that's your problem. You have to solve it.
So yeah, as we bring more of these data sets into the mix, Mark, that is the challenge that you're trying to address. How is the data that's currently being blended together being stored and processed? Can you talk a little bit about the Sigma Plus effort from that data infrastructure standpoint?
Sure. So we're using cloud-based computing and some of the best open source capabilities that exist. These are technologies that have been developed and leveraged by Twitter and LinkedIn and the like that are intended to handle the ingest, the messaging, the processing, the analysis, and the storage of vast amounts of sensor data. So think of Apache Mesos, Apache Kafka, Docker containers. Everything we do is in a Docker container. And again, it's all open source so that we're not dependent on a given cloud computing platform. That is, we can operate on Azure or we can operate on AWS or a private server platform. And with the capabilities that are availing themselves to cloud computing, these capabilities and systems and software continue to grow, and we're simply leveraging them. They're proliferating, and it's just great to be able to add on. Data storage costs continue to go down. Compute costs continue to go down. So all of that is really an enabler to what we're trying to do in Sigma Plus. The other critical piece of this is when you're talking about managing and handling heterogeneous data, whether it's different types of sensors or some of these additional contextual data sources, is now you've got to get into the realm of data curation. We heard about this on the last panel. A lot of that old historic data, as much as you'd like to use it, it's just not there in a manner, in a fashion that you can. And so we're developing data, what are called data schemas and ontologies, standardized frameworks by which, regardless of the type of data, it's being handled in an effective and accurate way so that these algorithms that we're developing, whether it's traditional kinds of statistical analyses of spectra, or of course moving forward, once you collect a lot of data, some of these advanced machine learning capabilities like neural networks and GANs, generative adversarial models, these are all then primed with the right kind of data and the right kind of format to be able to leverage these advanced analytical tools.
And this is a question for all of you. Are the standards mature enough that we can start to put these disparate data sets to use? And I'm thinking about the cities with their proprietary systems that you talked about, or Rick, there's even within an individual service branch, there's lots of different systems that may or may not talk to each other.
Yeah, so I can start.
Yeah.
One of the things we've been successful is latching on to other protocols and standards. So there's plenty of standards in the DoD for data transfer, data storage, data formats. Rather than create a whole new Cambio one, let's latch on to existing sensors. Now, that may take a little bit of code to translate our data, but that's far better than an entirely new data package. And of course, that existing data will be better integrated from the start with the existing DoD technologies. So again, we're sort of trying to leverage the existing and not create new, because there's plenty of standards and formats out there that we can utilize.
Mike?
We tend to key off of whatever DoD does because they have the money to do it, and we don't. And they have more expertise than we do. But it's the same issue, though, is how do you come up with standards for data integration, data transfer, huge areas, security, and you're talking to the nation, and it's all open because biodetection, especially on the terrorism side, equates with national security, but it really rests in public health. And public health, by its nature, is an open area. It has to be. So there are no really identified standards for us to use to say this is what your data has to be secure but open to everybody, and it's easily interpretable, but we're sending it all over the country, and we don't want the wrong people to see it. And so it's this paradox that we have to deal with that DoD doesn't have to, because they're dealing with a closed community, and they can insert those as security things because I only want you to see it, and you're going to be the only one who sees it. So, and it's just the reality of where we are.
And Mark, a little bit of an on-the-spot question. Just within DoD, is the Sigma Plus is at least talking to RIC's data sets at this point?
Are we talking to rich data sets?
Are you able to match up the data sets that Rick's talking about?
Well, right. Through this process of interoperability, for example, the ISA platform that CCD has developed, we are building the requisite roads to talk between the Sigma Plus, what we call Detect Network platform, and things like MFK and TAC, which are two very well recognized DoD common operating picture platforms, so that there is the ability to share information and display needed data and information between these disparate platforms. Okay. But interoperability is a challenge, right? Because these at local and municipal jurisdictions, they've got their own capability. So that's got to be enabled by obviously not just agreements between these various jurisdictions, but things like application programming interfaces that are fluid and dynamic to be able to adjust to the data needs and the data sources that we're trying to talk to and what we're trying to utilize as well. So it's a technical issue just as much as it is policies and politics.
All right. I had wanted to go to the data poisoning issue that Sterling raised and a few other things, but I want to make sure we leave time for questions from the audience. So questions for any of our panelists here this morning? Yes, sir. We'll bring the microphone in just a second.
Thank you. John Caves, National Defense University. Two questions. They're very quick. When I first got into business 20 years ago, there was an old saying that standoff biodetection is 10 years away and always will be. So, is it still a truism? And there's a lot of focus on advanced, emergent, and disruptive technologies. And one of them is quantum. And in the quantum area, sensing seems to be the earliest useful things that could be done in there. Is there any relevance to the WMD detection issues in the quantum side?
Any volunteers?
Don't look at me. I don't even know what it is.
I think we go to DARPA.
Rick,
for the
you want to do stand-up bio, and I'll do quantum.
I could do standoff bio.
Yeah. Well, I don't know if there's much to say in standoff bio. I alluded to the fact that we don't really talk about standoff anymore. We're looking at getting, perhaps because of technological reasons, but not necessarily, maybe you don't need to stand off. You can interrogate that threat with an unmanned vehicle. So we are looking at advances. There have been advances, but the idea that you would say from 30 kilometers away that's a cloud of anthrax. Well, do we really need that now? Maybe not. And again, I think earlier we talked about the 50% solution. If we can identify there's a cloud and then send a vehicle out there to interrogate it and perhaps do that autonomously so an operator doesn't have to see any of this, wouldn't that be just as good, if not better? And maybe you even get better data from the cloud, confirmatory data. So I think that's sort of the area we've been going with standoff bio, at least from a DoD perspective.
And then the other part of that with the whole my first thought when you said that was ask us in 10 years and we'll tell you. But the issue with standoff also was there was a hope you could identify what was in the cloud using standoff. And you can't, because you get fluorescence. Fluorescence is a physical measurement of microorganisms, and all bacteria look alike on the physical plane. And that really caused a problem. And from our perspective, it's not feasible in New York City because I'm going to collide with a building 2 feet away. And so the application of it became very, very limiting and very questionable.
Okay, and Mark, you should know that the final session is on emerging technologies, so if you want to punch, you're allowed to, but anything you'd like to say on the quantum front?
So just quantum research is an area of extreme interest in Defense Science Office. If you go to our webpage, you can look up some of the varied research activities in that space. But it's fundamental research, really, at this point. So it may, in time, lead to new innovative chemical and radiological sensing technologies. But right now, it's more fundamental research activity.
We have a question over at the far side.
Good morning.
Good morning.
My name is Ramira Rufus. I'm from MITRE Corporation. So from the title, trying to seek better detection tools, wow, I'm much louder than that gentleman. I wanted to know, this is my opinion, I think that the true kind of performance metrics that will come out of really evaluating these sensor capabilities will be based on the use case scenario, the usage scenario, right? But do you think that dealing with a sensory component and then the actuation component that would be its response, do you think you find better results from detection tools or capabilities that provide more granularity or more sensitivity with your ability to sense certain events, meaning it can be a collaborative effort, or do you think that you have more, which is more like an AI direction, trying to have a replacement of that kind of human cognitive processing, or do you think it's a better marriage of the sensory component with its actuation element, meaning that having better detection and more context from the sensory component? I think it's based off a use case scenario. What do you think? Or is that a loaded question?
The part on the bio side is we're dealing with something that exists in nature. And there's no way right now to go in and say that's Bacillus anthracis that someone released and that's Bacillus anthracis that lives here. And the other issue we have on the microbial side is there is a complete lack of standards on how much do you need to detect? How much is good enough? Because it really comes into which population are you looking to protect? Are we looking at the strapping 18-year-old Marine who could probably take a whole gallon of this stuff and catch a cold versus the 91-year-old lady in Hartford, Connecticut who died from a couple of spores? And the first thought is we're going to go protect everyone. So you're going to protect that 91-year-old lady, which becomes cost prohibitive and technically infeasible. And nobody has been able to come up and say, this is good enough, because no one's nutty enough to make that decision. And it's not a technical decision. It's going to have to be a policy decision, because we have the technologies, but someone somewhere has to say we have to cut it off here, and we'll absorb our losses. But nobody wants to make that decision. So kind of where you're going is, until those standards are generated, sensitivity is going to drive the train, just like it did when they first started doing water standards. It was my GCMS picks up 100 parts per million, Mark's picks up 30. So the standards are going to go from 100 to 30 because that's what we can detect. And that's quite literally on the microbial side where we are right now. Oh, and you're not allowed a false positive or a false negative, so don't be wrong.
Mark, Rick, any final thoughts on that question?
I mean, I would just riff off that sometimes we get ourselves in trouble with advanced sensor technology where we get so sensitive, and at some point doesn't really matter. If you're way below any human health aspect, doesn't matter that you detect it. And so we look at that both from detection and then even from decontamination. How safe is safe enough? And there's a political component to that, and then there's an actual human health component. And that can be a very complex issue. Telling someone, yes, there may be a chemical there, but you're perfectly safe. Well, I want it all gone. What is all gone when I can detect parts per trillion on almost any surface now with modern analytical technology? So I think we need to be very careful. There's big policy implications when you start talking about specific events. That's when it gets real. And a health limit sounds good in theory, but when you're talking about real people, and it becomes complex very quickly.
Mark, you're going to get the final word.
I think, if I heard correctly, how much does the actual stakeholders' concepts of operations and intended needs for monitoring and sensing affect desired performance and vice versa? Was that part of what you're asking?
Yeah, basically, the difference between wanting to, of course, AI replace the human or a component where we're just what's more digestible to us. A good example is like, okay, a dog whistle blows. We don't have the physical capacity to hear it, but my dog can. Mm-hmm. So what does that mean? For us, if it's endangering a human, is it a use case that we ignore that? Okay, that's not really going to cause us danger, but that sensitivity level that maybe my dog can register, right. Does it mean something? So which would you find what you want?
AI is a tool to help the human make a decision and to respond to what our sensors are seeing. And so there's an orchestration there by which we're not replacing the human, right? We're enabling the human with some of these artificial intelligence tools and capabilities. And if we can make sensors that are going to be more specific, more sensitive, augmenting, again, the human, and that's informing different AI approaches, I think that's where we're going.
And we are going to have to leave it there, but please join me in thanking all three of our speakers.